Good morning, students. Today we are going to discuss Fermat's principle from geometrical optics. Before going to study the Fermat's principle, we should have the knowledge of what is an optical medium and how does the light travels from one point to another point, and the phenomena of reflection and refraction of light along with their laws. So now we will go for the definition of Fermat's principle. According to Fermat, the path taken by a ray of light while passing from one point to another in a homogeneous medium is the path of least time. It means whenever light travels from one point to another point in a homogeneous medium, it will prefer that path which requires a very less time. Or the law can also be defined as the path taken by a ray of light while passing from one point to another in a homogeneous medium is the path of minimum, maximum time or stationary time. So the maximum time and stationary times are applicable to the different reflecting surfaces that we will discuss in our next slides. So now what do you mean by the rectilinear propagation of light? So rectilinear propagation of light indicates that the light always travels along a straight line because the straight line is the shortest distance between the 2 points. Hence, according to Fermat's principle, light travels along a straight line in a homogeneous medium. So as we all know that reflection is the phenomena where a ray of light is made to incident on a surface and it gets reflected back to the same medium. The same thing is illustrated in this figure 1.1 where we have a plane mirror on which a plane ABCD is held perpendicular. In this ABCD plane, there is a point O which is known as a point of incidence. The light is made to incident along PO and gets reflected along OQ where ON is the normal drawn to the surface. Hence, PO is incident ray, OQ is reflected ray and ON is the normal ray. All these incident ray, reflected ray and the normal ray, they all lie in the same plane here. Now consider a point R which is away from the plane ABCD and OR is being normal to the plane ABCD. Now a ray of light is incident along PR and gets reflected along RQ. From geometry, it is clear that PR is greater than PO, RQ is greater than OQ. Am I right? The geometrical path from P to R is found to be greater than PO and RQ is found to be greater than OQ. Hence, I can conclude that the total path PR plus RQ is greater than PO plus OQ, which is against to the Fermat's principle. Therefore, R must coincide with O. It indicates that the incident ray, the reflected ray and the normal all must lie in the same plane. Now the second law. The second law of reflection, as we know that the angle of incidence is equal to the angle of reflection. Now this we have to prove with the help of this figure 1.2. In this figure we have a surface XY which separates the medium from 1 to 2. O is the point of incidence. A ray of light is made to incident along PO. ON is the normal drawn and OQ is the reflected ray. The angle between the incident ray and the normal is taken as angle of incidence and the angle between the reflected ray and the normal is taken as angle of reflection. Here I and R are the angle of incidence and reflections. In order to derive the relation, we have made certain assumptions here. I have taken PO length as y1, OQ length as y2 and I have drawn PC perpendicular to xy and QD perpendicular to xy and the height PC is taken to be x1 and QD is taken to be x2. Now the time, if I want to calculate the time taken by the light to travel the path POQ, it can be obtained as T is equal to y1 plus y2 divided by c, where y1 and y2 are the optical length divided by c is the velocity of light. In triangle POC, if I take cos of I, so cos of I will become x1 divided by y1. So with this I can take sec I. So therefore sec I will become y1 divided by x1. In the same way, from triangle QOD, if I calculate cos R is equal to x2 divided by y2. From that I can obtain sec R as y2 divided by x2. So from these two relations, I can write that y1 will become equal to x1 sec I and y2 will become equal to x2 sec R. So substituting the values of y1 and y2 in my previous equation, that is a t is equal to y1 plus y2 divided by c, the equation will become t is equal to x1 sec I plus x2 sec R divided by c. So according to the Fermat's principle, the ray will prefer that path which requires least time. It means the dt must be equal to 0. So if I differentiate, then this the above equation will become dt is equal to 1 by c into x1 into differentiation of sec I will become sec I into tan I di plus differentiation of sec R will become sec R into tan R into dr. So therefore dt will become equal to 1 by c into x1 sec I tan I di plus x2 sec R tan R dr. Since dt is equal to 0, I can equate 1 by c into x1 sec I tan I di plus x2 sec R tan R dr is equal to 0. Then I can take the second term to the right hand side and I will get x1 sec I tan I di is equal to minus x2 sec R tan R dr. But from geometry, since the position of point O is constant, I can write CO plus OD is equal to a constant. If I take the tangent of I, so tan I will become equal to CO divided by x1. Hence, CO is equal to x1 into tan I. In the same way, OD can be obtained as OD is equal to x2 into tan R. So by substituting the value of CO and OD in the above equation, we get x1 tan I plus x2 tan R is equal to a constant. Now I will differentiate this equation. So after differentiating this, I will get x1 sec square I di plus x2 sec square R dr is equal to 0. Then again I will take the second term to the right hand side. So I will get x1 sec square I di is equal to minus x2 sec square R dr. So this I will take it as equation 3. So my equation 2 is x1 sec I tan I di is equal to minus x2 sec R tan R dr. So after dividing equation 2 by 3, I will get x1 sec I tan I di divided by x1 sec square I di is equal to minus x2 sec R tan R dr divided by minus x2 sec square R dr. By after simplification, I will get tan I divided by sec I is equal to tan R divided by sec R, which is nothing but sin I is equal to sin R, which implies I is equal to R. Hence, it means that the angle of incidence is equal to the angle of reflection, which is the second law of reflection. Next, we are going to study the phenomena of refraction. The phenomena of refraction, in the phenomena of refraction, the light travels from one medium to another homogeneous medium of refractive index n1 and n2. The medium 1 is known as rarer medium and the medium 2 is known as denser medium. Let xy be the surface which separates the rarer medium from the denser medium. I and R are the angle of incidence and refraction. PO is the incident ray and OQ is the refracted ray. Now again, I am going to calculate the time taken by the light to travel the path POQ as time taken is equal to distance travelled divided by velocity. Accordingly, T is equal to y1 divided by c divided by n1 plus y2 divided by c divided by n2. That implies time taken T is equal to n1 y1 divided by c plus n2 y2 divided by c. So this I will take it as equation 1. So in triangle POC, y1 is equal to x1 sec I and y2 is equal to x2 sec R. So I have got the values of y1 and y2 in terms of x1 sec I and x2 sec r. Now I will substitute the values of these y1 and y2 in equation 1. Then I will get t is equal to n1 x1 sec I divided by c plus n2 x2 sec r divided by c. Again, according to the Fermat principle, dt must be equal to 0. So I differentiate the above equation and I will get dt as dt is equal to 1 divided by c into n1 x1 sec I tan I di plus n2 x2 sec r tan r into dr. Now equating dt is equal to 0, I will get n1 x1 sec I tan I di is equal to minus n2 x2 sec r tan r into dr. Again, in the same way as we did in the previous derivation, CO, the distance CO plus OD is equal to a constant, since the point O, the position of O is a constant, where CO can be obtained as x1 tan I and OD can be obtained as x2 tan R. Now I will substitute CO and OD in the above equation. I will get x1 tan I plus x2 tan R is equal to a constant. So now I will differentiate the above equation, and after differentiation I will get x1 sec square I di plus x2 sec square r dr is equal to a 0, which can be simplified as x1 sec square I di is equal to minus x2 sec square r dr. So this I will consider as equation 3. Again, dividing equation 2 by 3, we get n1 x1 sec I tan I di divided by x1 sec square I di is equal to minus n2 x2 sec r tan r dr divided by minus x2 sec square r dr. So this can be simplified as n1 tan I divided by sec I, which is equal to n2 tan r divided by sec r. So this will give you n1 sin I is equal to n2 sin r. So that implies sin I by sin r is equal to n2 divided by n1, which is known as a well-known Snell's law. Dear students, so here we have shown that the Snell's law can be proved with the help of this figure. So in this session we had discussed and we had tried to understand and realize what is rectilinear propagation of light, and by using Fermat principle, so it is possible to derive the laws of reflection and refraction successfully. Now we have questions. We have some questions the same principle. So we have written certain questions. So among them I will discuss a few of them. The first question is, rectilinear propagation of light can be understood with the help of what? So rectilinear propagation can be understood with the help of Huygens theory is not possible, Newton's corpuscular theory is not related, and Fermat's principle is the correct answer. Dear students, follow the same thing and answer the remaining questions. Thank you.